Okay, so in the previous lecture, we proved that interval graphs are perfect. I hope the proof was clear to everybody. Any questions regarding that? Yeah. Okay, so we now look at a special type of ordering of the vertices for certain classes of graphs. So we begin a graph, and it contains a vertex whose neighborhood is a complete subgraph. Right? So its neighborhood, all possible edges are there between its neighbors. So if the neighborhood of a graph is a clique, then we say this vertex is a simplicial vertex. Now, suppose you have an ordering of the vertices such that so the first vertex that you delete is simplicial, then you find another vertex which is also simplicial. You keep on removing simplicial vertices till all the vertices are finished. Then we call that this ordering as a simplicial elimination ordering. Not all graphs have simplicial elimination ordering, and we will see. Like we will try to see what kind of graphs has this property. Now, so what we want is that when I am going to remove the ith vertex, right, in the remaining graph, this vertex is a simplicial vertex. Right? It may not be simplicial in the entire graph, but it is going to be simplicial in the graph on the remaining vertices. So here is here is an example. So you have a graph G, and so a simplicial elimination ordering for this. So I have given an ordering of the vertices here. If I pick the vertex V1, for example, right? Vertex V1, its neighborhood is a clique because it has only two neighbors, and they are adjacent. So V1. Okay. Then can I remove V2? I cannot remove V2 because the neighborhood of V2 is not a clique, right? Because V6 and V3 are not adjacent. But on the other hand, I can pick V3, for example, right? I can pick V3. If I remove V3, its neighborhood is a clique, so I can do that. Now I can remove V2 because its neighborhood is a clique. Now I can remove any of this because the entire thing is a clique, so I can remove, let's say, V4. Then I can remove V5, right? And I can remove one of these vertices, and that's it. So this way, you have an ordering which is called the simplicial elimination ordering. So we found one ordering. You can find another ordering. Right? For example, I could have instead started with V7 because the neighborhood of V7 is a clique. And I deleted something extra. I think I drew it. Yeah, I should not. It should not happen. So I removed V7. Then I can remove V1 again, maybe. Right? Then I can remove V3. I can remove 2. Then I can remove one of this, right? And the remaining. Just don't know why it's not working. I mean, some of the sometimes this acts quite crazy. Okay, anyway, you know that like you can remove the text and the remaining text. So such an ordering is called a simplicial elimination ordering. Now, one of our questions one can think about is that what kind of graphs have this property, right? You can of course try to build such a graph, right? You can start from a complete graph, right? And then because complete graphs have the simplicial elimination ordering, you know that you can start with any complete graph, and then you can basically introduce a new vertex and make it adjacent to some click, right, in this graph, any subset of any subset of vertices which forms a click, and then the new graph is not a click anymore, right? It's not complete anymore, but you can now take a vertex and add it to some subset which forms a click and keep on doing this. And if you do the reverse ordering, you will still get a elimination ordering. In fact, one can show that these are precisely the graphs which have the simplicial elimination ordering. So to come to this context, let us revisit something that we defined before. So a chord, of a cycle, right, in a graph, it basically we said that it is an edge that is not part of the cycle, but it connects to non-consecutive vertices in the cycle, right? So any such edge is called a chord. So here is an example graph, right, which has a chord, right? So in this graph, you can see that this edge is a chord, right? Because you take this cycle, this connects to non-consecutive vertices, so that's the chord. What else you can find? Is there any other chord? This is the chord. This cycle. Okay. Only this is a chord. If you look at the cycle formed by this. So a chord is basically such an edge, right? Now, if you have a cycle which does not contain any chords, then it is an induced cycle. Okay, the graph without any chords is an induced cycle, because if you just look at the vertices, of the cycle and look at the induced subgraph formed by this in the graph, then what you get is still just this cycle. You don't have any more edges, right? You are taking those vertices in the cycle, take the induced subgraph formed by these vertices, you will still get that same cycle, nothing else, no more edges added. So therefore, these cycles are called induced cycles or chordless cycles, because it does not have any chords. So here are two graphs, right? So the first one is a cycle which has no chord. Then the second one is a graph where every cycle is chordless. You can verify that each of the cycle you can find, for example, this cycle, right, or this cycle, or even this outer cycle, there is no chord, because this path is not a chord, because it is not a single edge that is joining, right? This is not a chord. Okay, so such cycles are called chordless cycles. Now suppose there is no cycle of length at least 4 in the graph which does not have a chord. Suppose every cycle which is an induced cycle is a 3 cycle, okay? Which means that there is no large cycle which is induced. In this case, the graph is said to be a chordal graph. Okay? So a graph is chordal if every cycle other than the 3 cycle contains a chord. So here are some examples. So in this first graph, right, you can verify that every cycle other than the 3 cycle contains a chord. So you pick any cycle, you can verify that it contains a chord. Right? And similarly, show that each cycle that you can come up with contains a code. So try to look at this kind of example and verify yourself that it is actually without any code, without any. I mean, each cycle has a code except for the 3 cycles. So for this graph also, right? If you take the big cycle, it has codes. If you take the 4th cycle here, it has a code. If you take any 4th cycle, it has a code, right? And even this 5 cycle has 2 codes like that. So each cycle, has a code except for the 3 cycles. So graphs are called chordal graphs. So this is a class of graphs, right, that you can define, and here are some more graphs, and I ask you to find which of these are chordal. So any answers for this, if you can tell me? Anyone? Okay, 2 is not chordal. Okay, fine. Okay, 1 is also not chordal according to Nishant. Okay, so 1 and 2 are not chordal because 1 has this outer cycle, right? Big cycle, and it has no chord. Similarly, 2 has the outer cycle, there is no chord. But you can try to convince yourself that the other 2 are actually chordal, right? Yeah. And 3 and 4 are actually chordal. So just try to work out and then show that it is actually chordal. So it's a nice exercise to think about. Okay, so now here is a theorem which says that the following statements are equivalent for any simple graph that we are considering. Okay. So the first statement is that G has a simplicial elimination ordering, that you can basically keep on removing vertices whose neighborhood is a click, till you get the empty graph. That is equivalent to saying that the graph is chordal, and it's also equivalent to a third condition that every minimal xy separator for non-adjacent vertices x and y induces a click. Okay. So if you take any pair of non-adjacent vertices in this graph and look at a minimal separator, right? There is no so basically xy separator we have already studied, a subset of vertices whose removal kills all the xy paths, right? So that is an xy separator, and a minimal separator is that no subset of this vertices is a separator, right? So take any minimal xy separator, then this xy separator, all vertices are adjacent, right? That induces a click. That is the claim. So each of these 3 are equivalent. That is the theorem. Now, how do we prove this? Okay. So we can try to prove like something like 3 implies 1, 1 implies 2, 2 implies 3, or some that should be sufficient to prove this claim. So we are going to do that. Okay. So first we will prove that 3 implies 1. So which means that if every minimal xy separator for non-adjacent pair of vertices induces a click, then we will show that the graph has a simplicial elimination ordering. So here is the idea. So pick up any induced subgraph of G. Okay. If you have any ideas on this, like you are also welcome to contribute. So just 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 ping me or raise your hand if you have some good suggestions on this. In any of the proofs you can do this. Yeah. So let H be an induced subgraph of G and consider a minimal XY separator in H. Right. So what we know is that it is basically a clique, right? So we have two vertices X and Y, and S is basically is is a minimal XY separator in the graph H. So H is basically a subgraph of G, okay? Not necessarily G itself, it's any subgraph of G. Now the claim is that this separator is contained in some minimal XY separator in the graph G also. Okay. So the claim is that if S is a minimal XY separator, in the graph H, which is an induced graph of G, then it is also contained in a minimal XY separator, right, in the graph G itself. So can you tell me why? Anand, any idea?
I'm not sure.
Okay, let me give you a hint. Yes. Yeah, tell me.
If you take a minimal XY separator in G and consider only the vertices in H,
Okay. Yes, that is true. But we are saying the other direction, right?
not contained in any minimal XY separator.
Okay. Okay, let me give you a hint. You can try to basically somehow augment or extend the minimal separator in in H to a separator in G, and then of course you can show that because because you can extend this, you will be able to find a minimal separator which contains this also, right? Okay, so here's the idea that if you have this separator, right, in H, you take all the vertices in G minus H, right? All the vertices in G minus H. If you add that vertices to S, then you get a separator in G, right? Some separator in G. Now, if you get some separator in G, you can basically remove, one by one from, which is outside, out of this, which is not necessary, and end up in a minimal one, right? It must contain S. Right? Because if it does not contain S, you can show that there is some XY path in this. So how do you do that? Okay, I want you to think about this and formally write from this, but it is precisely the idea. There is nothing more to it. So try to show this. Okay, so here is the Y questions. You fill up and then complete the proof. Now, suppose you show this, then the condition 3 holds for every induced subgraph also. What is the condition 3? That that every minimal XY separator induces a clique holds for every induced subgraph also. Okay, so again, try to complete the argument. Just write something to make sure that you can convince yourself and others that this is indeed the case. You should make it's not very difficult thing. Okay, let me tell you that if you just think about it for a few minutes and work out the details, you should be able to answer. Again, if you are not able to answer any of this, you must come back to me and let me know. Okay, so we can discuss this in any of the future classes. But it's important that you think about this now. So therefore, it's basically enough if if the graph contains some simplicial vertex, right? Because for every induced subgraph, the property is true. Then, if you can show that the graph G has a simplicial vertex, right? And then once you remove this, you are going to get another induced subgraph which has the property by what we just showed before, and therefore it will contain some simplicial vertex, and we can continue the process, right? So we just need to show that the graph contains a simplicial vertex to start the elimination ordering. Right? We want to produce an elimination ordering from the property that we assume, right? So, so we are going to now produce such a simplicial vertex. So if the graph is complete, we know that every vertex is simplicial. There is nothing to prove. But if the graph is not complete, we have a pair of non-adjacent vertices, and then we can look at a minimal separator for these non-adjacent vertices, right? And consider this to be the set S, and we know that S is a clique by the property, right? So we have a pair of non-adjacent vertices x and y according to what you see in the figure, and then what you do is that you remove the separator S, right? Separator S is a clique. You remove the separator S from the graph G. So after you remove this, you get several components possibly, and some component contains X, some other component contains Y. Now, what I mean by an S component is a component together with the vertices in S. Okay, so I add the vertices S back to that component alone. Right, I will discard all the other vertices right in the other components, but I take one of these components, put S together. So you take the component which contains X and put S together to it. So I get the S component containing X, which I call Gx, and Gy is the S component which contains the vertex Y. Now Gx and Gy are induced subgraphs because we have removed vertices to get these graphs. So we have two induced subgraphs Gx and Gy, and these two subgraphs, how they contain simplicial vertices by the induction hypothesis, right? So they will contain induction hypothesis by the induction, property, because we have got a graph which is strictly smaller. We have removed at least vertex Y, right, to get this. So therefore, we have smaller graphs, and we already know that induced subgraphs have this property 3, and from that we can show that they contain simplicial vertices, right, by using the induction hypothesis. But the base case is trivial, right? You can just look at the singleton case or like two vertices case, and then you have this base case. So I am not discussing it here. Now, what we need to observe is that these vertices that we have obtained, right, simplicial vertices, are also simplicial in the graph G also, right? So it's not necessarily always the case, right? If you pick any arbitrary simplicial vertex in a subgraph, it is a simplicial vertex in the graph, as a whole. But now we claim that in Gx and Gy, if you pick some simplicial vertices, they are also simplicial in the graph G. So again, can you tell me why? Or think about it and write about it. If you have any comments on this, you can tell me even when we continue the proof. So I will let you think. And otherwise, you can work out the details and write it down. And it would be a good idea because at least some of these proofs, it would be nice if you completely write down the proof on your own. We're completely filling up the details of why. And some of this you can share with me. I will try to look at least one of the proofs that you send me sometime. Okay. So suppose you complete this, then we are done, right? Because we have a simplicial vertex here in the graph G, and then you can keep on removing this, and by induction we get a simplicial elimination ordering. So prove 3 implies 1. So now we need to prove 2 implies 3, right? That is, if the graph is Chordal, then it has this property that any xy separator for non-adjacent pair of vertices induces a clique. Okay. So this is much more easier, right? So you consider any minimal xy separator in the graph G, and let's say that it is it's set S. So we want to show that S is basically a clique. Okay. So here is a picture which represents, like, you have some vertex X and Y which are not adjacent, right? And you have an xy separator which is a clique. Now, if you have a separating set, right? Now what you do is that you remove, the graph, the vertex at S, you get, some subgraph, right? Let's say hx and hy. Hx is one of the components which contains x, and hy is the component which contains y. Now, we don't put back s here, okay? This is not the s component we are talking about. These are just the components in G minus s. So hx and hy are the components containing x and y. Now, if you consider these components, then the claim is that, right, any pair of vertices, right, let's say u and v, you consider in the set S, they have neighbors in both hx as well as hy. Okay. So every vertex that you are going to pick up in S must have neighbors in hx as well as in hy. So again, can you tell me why?
It's not you can remove the vertex from the
Yes, precisely. Yeah. So, so because it is a minimal separating set, we know that this must be the case. Okay. So now once this is there, things are easy, right? Because, uh, if you pick any two vertices u and v in the set S, or maybe you want to complete the proof. So our purpose is to show that S is a clique, right? So how do you do that? Avinash? Anyone want to?
you can, because everything is connected, the neighbor of U and the neighbor of V have a path, and H have a path connecting them, and similarly in HY.
Okay. Mm-hmm.
And because your graph is ordered, that means U and V have to be
Yes, precisely. So, yeah, so there is a path starting from U to V which goes through the component hx. which means that it has at least two edges, right? And then similarly a path from U to V which goes through HY, which also has at least two edges, the edge incident to U from HY and the edge incident to V from HY, right? So at least a cycle of length 4, right? 4 or more is formed by doing this. So for this cycle there must be a chord, right? Because the graphs we are looking at are chordal graphs. Every cycle of length at least 4 contains a chord. Now the chord must appear from S, right? Because we are just looking at such a you can take the smallest path, and then we will end up in a graph without chords unless U and V are adjacent. And therefore, this is true for any pair UV. Therefore, you end up in the complete graph. So S is complete, and therefore we get 3. Okay, then we prove 1 implies 2, right? So 1 implies 2, we will no. So 1 says that there is a simplicial elimination ordering. So we start with a simplicial elimination ordering. Let's say V1, V2, etc. Vn. Now in this ordering, right? So you pick any arbitrary cycle of at least 4 vertices in the graph. So if every cycle is of length 3, then there is nothing to worry about, right? So if there is a larger cycle, we want to basically show that the graph is chordal. So we want to show that there is a chord. So if if you start with any any cycle of length at least 4, then the claim is that this cycle has a chord. So can you tell me why? Uh-huh. Yes, precisely. Yeah. So the first vertex that you pick up to remove from the cycle, and because it's simplicial ordering, its neighborhood must be a clique, right? Now, if you take any cycle of length that is 4, and if you pick some vertex, its neighborhood is a clique only if there is a chord for the cycle. So this is like very easy to see. So that is it. So if you want, I can even draw a picture, but I don't know whether I drew it before. No, maybe not. Probably I can work out yours. Okay. So now the reason we introduced chordal graphs are, again, we were looking at perfect graphs, and we claim that chordal graphs are perfect. So how do you show that chordal graphs are perfect? So first of all, it suffices that if you show for a given chordal graph G, if you show that the chromatic number of G is equal to the clique number of G, then that is good enough, because if you have a chordal graph, it's a hereditary family. So what is a hereditary family is all the induced subgraphs also belong to the family, right? So if you take a chordal graph and remove some subset of vertices, you cannot create a chord for cycles, right? By removing vertices, you cannot create chords. So therefore, what you cannot create chordless cycles, not chords. So you cannot create chordless cycles by removing vertices, and therefore, the graphs, induced subgraphs are also chordal. So therefore, chordal graphs form a hereditary family, and hence, to show that chordal graphs are perfect, it is sufficient to show that an arbitrary chordal graph satisfies that chromatic number is equal to its clique number. Okay. So now we are going to prove this by induction. Okay. So induction on the order of the graph, and when the order of graph is 1, the graph is a trivial graph, and it's the complete graph on one vertex, which is perfect, and there is nothing to prove. So we can assume without loss of generality that we are looking at graphs with at least two vertices, right? So cardinality of G is at least 2, and then we already know that there are simplicial vertices in this graph, right? So because it is chordal, so pick some simplicial vertex and remove this vertex. Now the claim is that the degree of the vertex x in G is at most the clique number of G minus x. So why is this true? So if you pick a vertex x, which is a simplicial vertex, right? Remove x, then you get the graph G minus x, and the degree of x in the graph G, right? In G is less than or equal to omega of G minus x. So why is this true? Well, it's pretty straightforward because the neighborhood is a clique, and that clique is sitting in G minus x. So the degree cannot be more than this, right? So therefore, it's upper bound by the clique number of G minus x. So we have chromatic number of G minus x is equal to the clique number of G minus x by induction, right? Let us say that this number is some k. Okay, so the chromatic number of G minus x equal to clique number of G minus x because we have a smaller graph, right, by deleting one vertex. So we have two cases, either the condition star, which is degree is less than or equal to is strict, or it is not strict. Okay? So if it is strict, then we know that we can color x using one of the k colors because the neighborhood has strictly less number of vertices than the number of colors that we have used. So therefore, one color will be free, and we can extend the coloring to this k coloring. Otherwise, the inequality is an equality, right? So therefore, degree is actually equal to this, and in that case, what you can say? If it is equality, then the clique size increases, right? And the clique size increases, there is no choice. We have to increase the number of colors, so we can introduce a new color to color it, and therefore omega and chi are again equal to k plus 1. Okay? So this is straightforward. Now this proof also tells you something, right? It tells that if you have this simplicial ordering, we can actually go in the reverse order and then give the greedy coloring algorithm, run the greedy coloring algorithm in the reverse order, and it will produce an optimal coloring, right? That is what that is how our coloring was going on, right? We color a smaller graph, then extend the coloring by looking at the minimum colors available, right? And if it is not, then we can introduce a new color, right? So this was the greedy on this. So therefore, the greedy algorithm works on chordal graphs to produce the optimal coloring. So a nice homework is to actually show that interval graphs are chordal graphs. Okay? And second question I give you to prove that any bipartite graph is given, then you can actually extend the bipartite graph to a regular bipartite graph, okay? Without increasing the maximum degree. Okay? So an arbitrary bipartite graph can be extended to a regular bipartite graph without increasing the maximum degree. So do this exercise. And then I have to think about a question in the previous class. And that is related to this very famous theorem called the perfect graph theorem. So this was proved by Lovash in 1972, just immediately after his PhD. This is defense, like within 1 year or something, and he proved this very interesting result and very famous result, because there was a conjecture called perfect graph conjecture, that a graph is perfect if and only if its complement is perfect. So we already observed that if a graph is bipartite, that is perfect, and we also show that its complement is also a perfect graph. Now it holds for any perfect graph, that is the claim, right? A graph is perfect if and only if its complement is perfect. And to do this, I ask you to think about a question that start with a perfect graph, let's say G, right? And take some vertex X. Okay. Start with the graph G and pick some vertex X, right? And then introduce a copy of X, which is called X dash, right? With the same neighbors as X, right? And then add the edge X to X dash, and you get a graph G dash. So this is the expansion of the vertex X. So you get a start from a graph G and expand it to introduce a new vertex, a copy of X, and to get a new graph G dash. So if I start with a perfect graph G, then the claim is that the expanded graph is also perfect. Did any of you work out this? Not yet? Okay, so lemma is the following. Before proving the perfect graph theorem, we need this lemma. Okay? So any graph obtained from a perfect graph by expanding a vertex is also perfect. That is what we want to prove. So we are going to use induction to do this. Okay, induction on the again order of the perfect graph that we are starting with. So we start with the graph on one vertex. Then basically we are extending it. So introducing a new vertex, again no neighbors, and then making them adjacent. So you'll get the graph K2, right? So you start with K1, you get K2. So of course, it is a complete graph. It is also perfect. So the graph obtained by the base case is done, right? Expanding K1 is also perfect. So what we do now is that you look at G at least 2 and start with some perfect graph, right? G. And then we have obtained the graph G dash by extension, right? Extended to introduce the vertex X dash. Now I claim that we want to show G dash is perfect. Okay. So it is sufficient to show that chromatic number of G dash is less than or equal to omega of G dash, right? The clique number of G dash. So why is that true? Yeah, reverse inequality is always true. So we just need to prove one of the inequalities, right? So now we want to show that G dash is perfect, right? We are going to show that chromatic number of G dash. We have a coloring using omega colors. So the first claim is that if you take any proper induced subgraph of G dash, right? Then, right, that is either a proper induced subgraph of G itself, right? In which case, because G is perfect, we know that this induced subgraph is also perfect, right? So if you take any proper induced subgraph uh, of G dash, it is perfect if it is a proper induced subgraph of G, right? This is an interesting way to use the induction, right? So if you take any proper induced subgraph of G dash, which is not a proper induced subgraph of G, right? But it is proper means that at least one vertex is missing, right? So if you look at any proper induced subgraph, If it is not an induced subgraph of G, then it is obtained by expansion of the vertex X from an induced subgraph of G. Okay. So this you need to observe that, like if you look at an induced subgraph, right? Induced subgraph in that you just remove some vertices, right? So either it contains X dash or not. If it is not containing X dash, then it is basically an induced subgraph of G, in which case, because G is perfect, that is also perfect, right? Now, if not, then it contains X dash, right? Which means that, you know, the subgraph that we are going to look at, will be missing some vertices other than X dash, right? But then it is obtained from, expansion of some subgraph where we have basically expanded the vertex, vertex X to get this, right? Now, if X is not part of it, then, and X dash is part, then it is identical to having just X, because, X and X dash are exactly the same. So therefore, we can say that, we can now use induction, because every proper induced subgraph of, G is perfect. And if you do an expansion on that by induction hypothesis on a smaller graph, again we get a perfect graph by this property, right? So this is a very, very nice way to use the induction. So once you have this, well, we start with the click number, and then we are going to give a coloring, right? So look at the click number of the graph G to begin with, right? Then what is going to be the click number of the graph G dash? So G dash, we have introduced only one new vertex, so the click number cannot increase by more than one, it cannot reduce. So therefore it will be either T itself, or it is going to be T plus 1. Okay, our time is already up. Okay, so let me just try to give you a gist of this. So basically, we are saying that if you are going to introduce, if it is the click number is the same, if the click number is increasing, then we can always introduce a new color, right? So that part is immediate. If the click number is the same, then we have to show that we have a coloring with T colors. So for this, we will just just observe that the vertex X is not part of a complete graph on T vertices in the graph. Okay, and then you will be able to extend the coloring to this. So how do you do that? So for that, we use the following property, right? So if you have if you have this graph G, and we have a coloring, right? Using T colors. Look at the color class of X, right? So the color class of X here I have marked with yellow, right? Is an independent set, which I call as X. Okay, so the independent set for the color class of containing X is called large X. Now this set, we can observe that the vertex X cannot be part of any complete graph on T vertices, because otherwise when I introduce X dash, the click size will increase. So therefore, no complete graph on T vertices will intersect with that vertex X. But because because we are only using T colors for coloring G, it must intersect the color class X somewhere. So it can only intersect in some vertices in X minus singleton X. So every click must intersect X minus X somewhere, right? But it cannot intersect X, right? Because otherwise the click size will increase. So using this property, what we can do is that we can essentially come up with a recoloring, right, of the graph obtained by removing X minus singleton X from from the graph G, and because it's an independent set, once I introduce the new color, you have a coloring. So now the point is that once you remove this, because it is intersecting every click, right, the click size will reduce by 1, at least 1, right? So the click size will reduce because every click of size t will intersect one of the vertices in x minus singleton x. And once you have the smaller click, you have a coloring with less number of colors. You color that, but now you observe that x minus singleton x is an independent set, and adding x dash also to it also keeps the independence property, right? So now I can put x dash to this set and use just only one color to extend the coloring to this to this graph on using only t colors, t or whatever I use k colors, right? I think I use t somewhere, k somewhere. It will be t. Yeah. So that is it. So that way we can so here I have written it down. So G is perfect. We can color with k minus one colors and then basically extend it to v minus, v of g minus h is independent set because we have just observed it, and then we extend the coloring to this. Okay, I think I will wind up here today, and next class we will prove the perfect graph theorem. Okay, so that is the idea. So any questions, please feel free to ask.